Yeah, so I will talk about modeling of variability with SysML v2, and I'm Tim Weilkiens from oose. So as Charlie Kruger said, he's one of the product line engineering pioneers and CEO of Big Lever. He said, nobody builds just one system. So variability is the norm, and the system family should be the system of interest instead of just a single system. Okay, so let's talk about variability. And the modeling of variability with SysML is already a topic since SysML exists. And SysML v1 has no explicit support of variability modeling. However, you can use it to model variability. And in particular, a modeling language should support the concept of generalization or specialization for variability modeling. And that's the case in SysML v1. So that's more than 10 years ago, I wrote a book about modeling variability with SysML v1 to prove that it works just with the standard language. So there's no need for special tools or so. Now SysML v2 has explicit support for variability modeling. And well, there's a famous quote, that's one small step for SysML. There are only a few model elements in there, but it's one giant leap for MBSE. And it was time for another book. Well, I write a lot of books. I wrote this book together with Marco Folungiri, who's the chair of the NCOSI PLE working group, and Guillermo Chalet, who is the head of PLE at Airbus. So it's model-based product line engineering. It will be available in 1 or 2 or 3 weeks. But let's start with modeling variability with SysML v2 and how it's related to PLE. So a simple guide, example will guide us through this talk. We will look at a drone manufacturer that has been contracted to develop a system of drones that can transport smaller packages to ships that anchor outside in the harbor, medicine or whatever what the crew needs. And of course, the example here is greatly simplified. The models must fit on my slides, and they must be understandable in this short time available. And of course, I could use larger models, and maybe it's more impressive, but you would only understand the half of it. So let's start with a very simple version of our drone system. And I will focus on the structure. I skip the requirements and the behaviors, and the concepts are the same there as in the structural world. So here's a simple architecture of our drone system. It consists of many drone docks, so for charging the drones and landing and so. Many drones and a control station. And the drones are defined by the part definition drone, which has 4 engines, a battery, and a body. So very, very simple. Well, in real projects, as Charlie said, we typically build a family of systems. And our initial idea of a single delivery drone was quickly turned into a family of systems by our customers with new requirements. So they would like to see different types of drones with different numbers of engines and with different attachments for small payloads and large payloads and all this stuff. So our architect creates a new architecture, a revised version. And I skipped the payload attachment here on this slide for now. And this model allows now different kinds of batteries and a different number of engines. So we have variability here, but we have not used any specific variability model elements yet. So typical elements to model variability are multiplicities. So this model allows 4, 5, 4, 6, 7, 8 engines. And we have here the specialization relationship to model 2 different kinds of batteries. So however, this model leads to several open questions. Assume we hand over this model to the production, they will have for sure some questions. So for example, this one, I don't think that a drone with 7 engines will work well. So how many engines should we build in the drone? We said 4 to 8. Or this one, which kind of battery should we use? We have 4 different kinds in stock. In this version now, the part def battery is part of a library, and our library defines 4 different battery kinds: a standard battery, power, X power, and small battery. So we need to be more specific in our model. And well, we can use the SysML 2 variation and variant concept for it. So here you see the next version of our model. This time we also have included the different payload attachments, small and large. And you see the variation and variant concept. So a variation here on this side, for example, a variation is also known as a variation point. It's the same in SysML 2. So it's the point where someone has to make a decision for some design options. And the design options are defined by the variants. So in this case, we have 4, 6, or 8 engines and specify them with a clearly defined multiplicity, 4, 6, and 8. So let's have a more detailed look on this concept of variation and variance. Variation and variance are not individual model elements in SysML 2. In the background, it's actually a relationship. It's a relationship between the variation, so our engines property at the top, and the variance. And the ends of this relationship define that the source element is the variation and the target element is the variant. And then we can use this concept for any usages in SysML 2. We can do the same with requirements, with actions, with states, and so forth. And the variant membership relationship is visible here by this keyword attached to the keyword of this element. So we have variation part and variant part, and otherwise it would be a variation requirement and variant requirement and so forth. This variant membership is also a membership relationship, and that's why we see here this membership relationship, the containment relationship here on this in this model. Yeah, of course, our variance must be conform to the variation, because wherever we use our variation, I can insert one of our variants. Also, wherever I use engines, I will later inject, so to say, one of the variants and say, okay, I have decided that we use 6 engines. So they must be conform to each other. It has a touch of specialization, generalization, but it isn't, but it has a touch of it, and there are corresponding rules about this in the background. Yeah, so this is the textual notation of the variation and variance. It's straightforward. You see the keyword variations and variants before the part keyword here. And as I said, it works similar for other elements like requirements, actions, and so forth. Here at the end, we have also added a constraint that now assures that when the engines is not the 4 engines variant, then the battery must be a power battery. So these are these typical feature constraints, if you're a little bit familiar with PLE. And this is how we define them here in the SysML 2 model. And it's not a special variability model element here, it's just the SysML 2 constraint. It's not specific to variant modeling. So let's now specify a concrete product, and it's our delivery drone system X42. And it has 6 engines, a power battery, and an attachment for large payloads. So here it is, the graphical version of it. So it specializes our part def drone system, that's the common part. And now it redefines all the variation elements, and by binding sets the selected variant. So you see here, this one. The engines is 6 engines, the battery is power battery, and the body contains the payload attachment, which is now the large payload attachment. And the same here in textual notation, and you see there are no variation and variant elements now here anymore. But here you can clearly see the design decisions, no? Engines, battery, and the payload attachment of the body. And well, that's it more or less in SysML to model variability. It's a simple element, very powerful, a small step in SysML, but it has a lot of impact. And of course, we must not, well, my presentation is not over yet. We must not forget that there is more than SysML in the engineering world. I know that's hard, but there are other things. As for example, well, requirements are often not modeled with SysML, simply stored in text documents that's still out there, or in a requirements management tool. Or a software, as Doug Rosenberg says, there's no system without software. Source code is a crucial part of a system, and it's not specified in SysML in most cases, or mechanical design, and so forth. And all these artifacts are also impacted by the variability. So if we decide for 4, 6, or 8 engines and all the other stuff, it has an impact also on these artifacts. So how does this fit together, the modeling in SysML v2 of the variation variance with all the other engineering artifacts? So let's leave the question of variability aside for a moment, and let's have a quick look on the challenge of the digital thread. And Ed and Manas already talked about that. And SysML plays here a crucial role in the digital thread. It's the backbone of the digital thread. So a typical challenge is here. You have requirements, or many of them, and they are linked to software, because the software satisfies the requirements, so you need some kind of traceability link. You have CAD models, they also satisfy the requirements, and maybe in the software is hard-coded some length from parts or whatever. So there's also a relationship. We have safety analysis, simulation models, sustainability modeling with OpenLCA, and so forth. So I guess you know that one, this game, and it's a nightmare. No? If something is changed here to keep everything in sync, that's a nightmare, and a lot of errors happens. And SysML v2, well, plays this role. It's in the nature of a system model to integrate everything. Everything needs a direct or indirect anchor point in a SysML model. So it has this integrative role and is a kind of a backbone, so to say, for our engineering of the digital thread. You must not misunderstood this slide here. It looks like that SysML is a central model. That's not the idea here. It's more the glue logic between all the other models, but it's hard to show the glue logic on a slide. I tried it several times, so it does not work very well. So it's not a central master database. It's the glue logic between all our engineering tools. And of course, the engineering tools itself and models can also be connected directly without going through the SysML world. Yeah, and connecting things, well, we have this sparkling, game-changing feature, the SysML v2 API and services, which enables the model interoperability much more. Manas already did a great job of presenting this earlier. So there it is, the SysML v2 API. So it's much easier now to connect the engineering tools to the SysML model. You should not forget that in addition to the API, on the SysML side, all the engineering tools also need something to be able to connect to the API, and much more important, to understand what they get from the API. And they get a JSON data and must, of course, be able to read the data and understand the data. So all the engineering tools need some kind of SysML v2 capability, plugin, whatever. So let's go back to the variability. Don't worry, I will merge the topics later. So here you can see our drone architecture with the variation and variance again. And here you see a similar picture of the features. And now be careful, the term feature, it's a feature tree, they have different meanings. So a feature is an element, has a different specific meaning in SysML, but here it's different. Some people also use the term feature and requirements engineering. That's also a different one. So this is the term feature here on this slide in the world of PLE, product line engineering, the feature trees. And the feature is there represents a distinguishing characteristic of a system. So it defines the variability of my system. But it looks quite similar to the variation variant part, but it's different. So to show you the whole picture, there's a standard, 26580, the ISO standard that defines the feature-based product line engineering world and all the pieces there. One piece is the feature model with the feature tree, like the one I showed you before, and the feature configurations. A feature configuration is a selection of features. So for a specific drone, for example, I select this, this, and that. That's a feature configuration. And we have what the standard calls the shared assets superset. That's the set of all our digital engineering artifacts, requirements, architecture, whatever. Everything is in there, including our SysML model. So here's our SysML model that I showed you before. It's in the shared asset supersets. It's not in the feature world. And then that's the idea. Theoretically, it's great. There's some magic PLE configurator that gets a feature configuration, selects the corresponding part in the shared assets, and automatically creates a product model. So I think I see on the slide, yeah. So our drone architecture is in the shared asset supersets, and this delivery drone X42 that I showed you before is one concrete product model. And we have not modeled a feature tree yet. So how does this fit together? Let's go back to this picture. With our SysML model, which is in the shared asset supersets, plays this integrated role of all our engineering artifacts. But now, in addition, we have this feature tree thing. A feature tree defines the variability of my product line and has an impact in all the engineering tools. I need this information in my CAD model. I need this information in the requirement model. I need this information everywhere. And my SysML model, of course. So here we have another central element there, the PLE tool. And there lives the feature tree and the feature configuration. So now my CAD tool and the other engineering tools must connect to the SysML tool for this integrative thing, and connect to the PLE tool to get this variability information. And all these tools also need some kind of PLE plugin to use this information, this variability information, to automatically filter out unwanted features and so forth. And very likely, these two worlds have two different connection technologies. We have the API and SysML v2, and we have typically some tool vendor proprietary technology on the left side here. So now imagine we integrate the feature model in SysML v2. That would simplify the digital thread. So now the connection technology is SysML v2 API, but of course we still need PLE functionality in the SysML world at the top, and we need PLE functionality still in our engineering tools. So, but how do we get the features into the SysML world? Well, I had explained it before. We can define a language extension and define the feature concept and then use it in the language. So a disclaimer up front, the following is not final. We are still in the laboratory doing experiments. It's just a proposal. And in this laboratory, you will find, beside others, this guy here, Marco Folunghieri. I mentioned him before. He's one of the co-authors of this book and the Incosi PLE working group lead. So he's responsible for the PLE stuff and says, oh, in PLE, you typically do it that way. I'm also in the lab and do the SysML v2 stuff. And another one is in the lab, that's Vince, is also in the lab. And he takes care that everything is formally correct. So that's typically our roles in the laboratory. So I have an idea. Marco says, no, 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 in PLE you do this differently, okay, change it. And Vincent says, no, that's not formally correct. So, and what I show you next is our current version. We had some versions before, and there will probably other versions in the future. So we use the SysML2 language extension to define features in SysML2. So this is an example. We call it PLEML, the product line engineering modeling language. And it's a very simple extract of this library here, just an example to show you the concept. A feature, for example, has a binding time that specifies when I have to make this decision in my engineering process. So I can make this decision during the development phase, or I can make it during the production phase, or maybe I can do this decision in the operation phase. So we defined an enum here in our library, and then at the bottom you see our feature concept. It's an occurrence definition at the moment with an attribute with this binding time, and the default is development because that's the typical binding time. Yeah, we have more sophisticated stuff in there to define the feature constraints, for example, and you see here the beauty of the expression language of SysML2, accessing library elements and so forth. So that's in our library. And then we can use it. This is a simple feature tree with this feature keyword. So here you see our battery feature with a binding time. We decided, well, that's production. The production can decide the battery kind. Maybe you realize that there are different kinds of relationships. We have composition and specialization. That's our current approach. We also had other approaches how to model features. Vince and I like this approach currently very much. We are pretty sure that Marco will not like it because it's not like a feature tree. So that's our next discussion. But this, yeah, for us, it works very well. And here the same textually. So with the keyword feature, we have the feature tree, and it contains the feature battery and the standard battery and the power battery. So in a real project environment, people probably would not use the SysML, the pure SysML modeling tool capabilities to create textual notation or the graphical notation. With feature trees, they need some convenience functions for feature modeling. So there must be some special feature modeling capability in the tool. And it can also be that SysML is invisible for the user. They create their feature trees, and in the background is SysML. But everything's possible there. So here's the full feature tree graphically, but nothing new in there. It's the same, but larger with all our features we had so far. And here's the feature configuration, only the textual notation. Now we have a feature configuration at the top. It's the delivery drone. And a feature configuration specializes our feature tree and then redefines the decision points and sets then the concrete feature. So the delivery drone has an X power battery, a power charging functionality, 6 engines, 1 camera, has the camera patterns flight strategy, and has the payload capability. And then we need another one. You see here in my overview picture. It's complete here. Here's the feature tree at the bottom, the corner, and we have a relationship to the shared asset superset here. So we need a link between these two, and that's the feature binding. So if we link our features to engineering artifacts which are also in SysML2, we can describe this link in SysML2 directly. We don't need an interoperable connection between feature tree in SysML2 and CAD models in whatever. And here's the feature binding. So the left element of this connect statement is in our architecture on the requirements world. So that's our shared assets model. We have the drone system requirements, the drone product control unit thing. These are functionalities, actions. And at the bottom, you see the drone product battery. And it's not completely in the slide because it's too long, but on the right side are the features in the feature tree. So this is how you can connect the elements if they are in the same model. So, yeah, finally, oh, I'm good on time. Oh, yeah. I can show you some brief demos how to use now this model. The model is at the top in the SysML v2 world, how you can use this model and the API. And I will not do live demos because, well, they typically fail. So it's just screen cuts, but it's real. So there's no AI tweak in there, except that I shortened it a bit. The performance is too low, so I increased the speed a bit. So the first thing I did, I created a website to access the repository there, to read out the stuff. So this is the website, and you can select the server. It's the Intercach server. You get all the projects. I can select the project. That's my drone project. It's there. Then I have to select the commit, and then I can retrieve the feature tree. So it reads the whole model and then looks for the features. And here there are, it's quite small, but this is a feature tree in textual notation and in ASCII notation. And we can do the same for the feature configuration. So we get here, I think we have three feature configurations in the model, and it lists the elements that are selected for each feature configuration. So that's my test website, so to say. There's also AI, but that's another topic. But that's, of course, it's easy now to get this information, throw this information to ChatGPT, to another API, and say, is something missing? Is there a misunderstanding? Whatever. So I did also some experiments with that. So it's quite simple to do that and very helpful. But that's not the topic here. So another example. Let's assume we have our requirements in Word. There's still projects that work that way. And the text now contains textual annotations. Well, then in the text document, I must tag somehow my text that's only valid for a single feature. So and it's here, well, it's quite small, but some texts have these tags like in HTML. So start with the feature name, then comes the text, and then it ends with a closing tag for the feature name. And I created a small Visual Basic script. It's quite easy to do that. It's a plugin here in the Word, feature configuration. I can then connect with the API again, and then I get the list of feature configurations. I can select a feature configuration, and then I get the list of features. Well, and then I can highlight the requirements in my document that are valid for those features. And there's another button, then I can filter out the other ones. And at the end, I have a Word document only for this feature configuration, and all the others are filtered out. That's the typical functionality of a PLE tool. And last one, well, this is a PLE tool. It's not a commercial one. It's Feature IDE. It's an open source PLE tool. It's Eclipse-based. So I wrote a plugin for that one, and it can access the API. Now it's empty. I can access the API and say, load the features from the SysML model, and then I get the feature tree in the tool, and it's there. Of course, it's also possible the other way around. I can change now the features here and write this back to the SysML v2 model. So as a feature modeler, I still use my favorite feature modeling tool, if it's this one. I create my feature trees with all the stuff, but in the background, the information is written into the SysML world. Yeah, these are only short demonstrators. It's not a product. Actually, I wrote these 3 plugins in 4 hours together with my friend ChatGPT. So I'm not a programmer anymore, not a good one at least. I had this idea. I went running, had this idea that, oh, I must do this, come back, and 4 hours later, this was ready. It's quite easy to do that. Yeah, finally, now we have many options how to use this now. So how to weave our digital thread. No? And here's one option. It's probably the standard options nowadays. So we have in this example, a requirements model, we have a software model, we have a simulation model, and they are integrated or linked together in our system model, which is SysML, and the green line shows, okay, we have the SysML v2 API there, that's the connection between these models. And then in addition, we have a feature model with the feature information, and that one is also connected to all the other tools, including SysML, to push this variability information into those engineering tools. And it's another technology, some PLE connection technology, though. That's one option. The second one is that I showed you before. Now the feature model is also in SysML. It's a SysML model. And now the connection technology is the SysML v2 API. And not shown here on this slide, of course, my requirements model needs still some kind of PLE functionality to understand the information that it gets from the feature model, of course. So that's another scenario. But there's a third one is here. Well, maybe the world is not black and white. This is black and white. In the extreme scenario, what happens if the feature model is only connected with our SysML model and controls the variability in our SysML model? So in this connection, we create then a SysML product model, and the other engineering tools are then connected with this product model. So there's no direct connection to the feature model anymore. Maybe this works also. For some cases, maybe for all cases, that's under discussion. And for sure, there are other options, and so forth. Yeah, but there's more than variation and variance in SysML v2. It's extremely powerful to model now variations in SysML v2, but then we are in the shared asset superset world. It's not about modeling of features, how is like it's defined in the feature in the PLE world. And that's different, but you can add features to SysML, as I showed you before, and then use it in different ways. And with that, I'm at the end. I think that's the last one. Yes, that's the last one. So, and we have, I think, some time for questions.
Thank you, Tim. So here I apply this Hans-Peter de Koning consult. Here you apply the variability to product line engineering. I think we can all use almost exactly the same patterns for design exploration on options of different design alternatives.
Yes.
Did you think about that, or do you see any differences?
It's possible, but we have not investigated on that.